Welcome to part 2 of section 3.9. We've been talking about chemical analysis. And we have gotten out of the system. So sorry about that. So let's look back here. And we've been looking at chemical analysis. And what we have to realize is that, let's say we have an unknown amount of something known, and we react it with something else that's a known amount of a known substance, and we make a new substance of known ratio, this empirical formula. We can back calculate then this unknown amount of a substance. And so we're going to be looking at this mass conservation theory that we learned in chapter 2. And so let's say we have an impure sample that has sodium sulfate contained in it. And so we have a sample that part of it is sodium sulfate and part of it is something else. Okay, and the mass of the entire mineral sample, okay, is 0.123 grams. Now, the sodium sulfate in the sample is converted into insoluble, meaning it does not dissolve in water, barium sulfate. Okay, and we'll look at that chemical equation in just a minute. And the mass of barium sulfate was found to be 0.177 grams. How much of the original sample is the sodium sulfate in mass percent? And so what we need to look at, first of all, is a chemical reaction that will convert sodium sulfate into barium sulfate. And so you would be given that equation at this point in our lives, because we haven't really learned on how to make or balance chemical equations yet. We're going to learn that in section 3.10 or 3-10. So here is a balanced chemical reaction. Actually, if we balance it, we're going to put a 2 in front of there, and so then we should be good to go. But the AQ means aqueous. Means that it's dissolved in water. The S here in parentheses just means a solid. And so that means that it's not soluble or insoluble. And so this is what we're making. So we're converting sodium sulfate into barium sulfate. Now, what we have to look at in chemical analysis is the ratio between two chemicals. For example, we're looking at sodium sulfate turning into barium sulfate. And it's a 1-to-1 ratio according to the balanced chemical recipe, the equation. So we can write a conversion factor that says for every 1 mole of sodium sulfate that we react in the original mineral, we will make 1 mole of barium sulfate. And we're going to use that as a conversion factor. So the very first thing that we're going to do is we are given that we made 1.77 grams of barium sulfate. Let's get that into moles. So if we look at the molar mass of barium sulfate, for every 1 mole, remember we get this from the periodic table, and we're not rounding off any of those numbers. And then the barium sulfate grams will cancel. Now we have moles of barium sulfate. And so we can use the balanced equation when we're talking about two different chemicals, and we're going to be looking at this in more detail in chapter 4. If we're looking at two different chemicals, we use the balanced chemical equation to relate one chemical to another. And so as we said up here, 1 mole of barium sulfate, in order to make it, will require 1 mole of sodium sulfate to make it. And so we're going to use this conversion factor, which is called a mole-to-mole conversion factor, to cancel out the moles of barium sulfate. Now we have moles of sodium sulfate. Now, do not write this as 1/1, because 1/1 is not the same thing as 1 mole of sodium sulfate over 1 mole of barium sulfate. So this is where writing down the chemical formulas of all of your conversion factors is going to help keep you straight to see what will cancel out. So please be aware that you must write down moles of sodium sulfate, moles of barium sulfate, the formulas. Now you have moles of sodium sulfate. We want to know how many moles were in the original sample. So how many grams were in the original sample? So we have moles of it, so we'll use the molar mass from the periodic table. So this comes from the balanced reaction. And we will find that we made, or will need, 0.108 grams of sodium sulfate was needed to make the 0.177 grams of barium sulfate. So that's what was present in the original mineral sample. So in order to get the mass percent, we're going to take the original amount then in the mineral over the entire mineral mass, because the original amount is the pure sodium sulfate. That's what actually reacted to make the barium sulfate, whereas the mineral has a whole bunch of other junk in it. And so part over whole times 100. So we're going to see that it's 87.58%, and we want to write down the chemical formula, sodium sulfate. And so we have to have percent of what chemical. So that's cool. We can use chemical analysis then to determine percentages. So here we have heating a 1.7184 gram sample of sodium hydrogen carbonate gives 0.196 grams of carbon dioxide. What was the amount of sodium hydrogen carbonate in the original sample? And so they're saying that this may have some other stuff in there. And so let's look at this particular equation. So first of all, the equation is balanced, okay? And so we're looking at sodium hydrogen carbonate, and we're also talking about CO2. And so we're looking at comparing these two chemicals. If we're going to do that, we need to write down for every 2 moles, okay, because that's what this 2 in front means, of the NaHCO3, that's going to equal 1 mole of the CO2, according to our balanced equation. It's a 2-to-1 ratio. There's a 1 out front of the CO2. We just never write the 1. If the formula is written down, it assumes we have 1 mole of that in the balanced equation. So we know what we have as a product here. So let's get that into moles, because I don't know what I'm doing. So at least I'm in moles, and these will cancel out the grams of CO2. Now we have moles. So in the balanced equation, for every 1 mole of CO2 that we make, we needed 2 moles of sodium hydrogen carbonate. So we're going to use the mole-to-mole conversion. So this was from the periodic table. This was from the balanced equation. And remember, the molar mass is always by definition 1 mole of something. Okay? This does not come from the balanced equation. Now, the moles of CO2 cancel. Now we have moles of sodium hydrogen carbonate. Now get it back to grams. So this comes from the periodic table, and it's per 1 mole. I don't care that there are 2 moles in the balanced equation, because the mole-to-mole conversion factor takes that into account. Molar mass is always by definition per a mole. And so we'll see that originally then we had 0.748 grams of sodium hydrogen carbonate. Well, the sample we burned is much bigger than that. So to get the percentage, take the part that is the sodium hydrogen carbonate only over the whole sample times 100. We get 43.5% sodium hydrogen carbonate. Now, if we look at this, I'm going to get rid of my pen here. There's a couple things that we want to look at. So I'm going to bring my mousey here. Well, there we go. Oh, we have an ad.
The candle is a hydrocarbon. The hydrogen will...
Okay, so what we have here is a chemical analysis problem where they're showing any candle that's made from carbon and hydrogen only and burning it in excess oxygen. So we have O2 plus a hydrocarbon, And then we're going to look at how much CO2 we made at the very end. And so this is another way to look at these combustion analysis problems. Anything burning in oxygen will make water and carbon dioxide. So we can determine, trapping the water and the carbon dioxide made from a chemical reaction and weighing them, how much carbon and hydrogen are going to be present in the original hydrocarbon. So let's listen.
React with oxygen in the air to form water, H2O, in the form of vapor. It will be absorbed by the water absorber, release and percolate, and any increase in its mass will represent the water vapor produced. The carbon in the candle will turn to CO2. It'll pass through where it will be picked up in the second of the U-shaped tubes, so any increase in its mass will be the mass of carbon dioxide produced. There's a suction pump to the right which will draw the products of combustion through the two U-shaped tubes. If you look, you'll see separately there's a carbon dioxide molecule being produced. It passes to the second of the two U-shaped tubes. There's a water, passes and is absorbed in the first of the two U-shaped tubes. Let's have a look at the equation for the reaction. C reacts with O2 to form CO2. The H2, the hydrogen of the hydrocarbon, reacts with oxygen to form H2O. And to balance the equation, you need 2H2 reacting with O2 to give 2H2O. So C turns to CO2, H turns to H2O. Let's take a look at one of these combustion analysis calculations.
Okay, so I'm going to stop that. You should watch this video on your own. We're not going to watch it here because it'll just add time to ours. But make sure you click on the link in your PowerPoint slides so that you can go to watch this particular movie, because he does talk about all of the hydrogen in the hydrocarbon then goes to make water. All of the carbon in the hydrocarbon goes to make CO2. And so we're going to do a very similar problem in the PowerPoints. So this is just another way to solve this problem, and maybe a better explanation than mine. So go and watch that. So we're going to go back here and go back to our PowerPoint slide. And this is just another way to look at this. So if we look at this YouTube video, this guy is awesome. He's from Montana.
Hi, it's Mr. Anderson, and this is Chemistry Essentials Video 2. It's on chemical analysis. One of the first early chemists, Jöns Jakob Berzelius, who was Swedish, came up with the way that we write out chemical formulas. And I love this picture here. It's one of those where no matter where I move, he seems to be watching me. But, so when we write out CH2O, which is actually going to be the empirical formula or the simplest formula of a sugar, let's say glucose, we owe it to him for that. But if we look at the actual structure, this is what glucose looks like. So it's going to have 6 carbon, 12 hydrogen, and 6 oxygen. But chemical analysis is simply looking at a compound like glucose, for example, figuring out what's in there, how much of that, what, and then how it's all connected together. And so in chemical analysis, we're looking at compounds. And remember, compounds are going to be made up of atoms, and each of those atoms have a specific mass. And so what we can do is look at the percent mass. In other words, how much of that mass of that compound is made up by each of those different atoms. That tells us what the composition is. It also can help us figure out the empirical formula. That's that simplest chemical formula. And it also can be used to test the purity of a substance. In other words, is it just that, or are there other things that are added inside there? And so let me give you an example, and we'll come back to this at the end of the video. Let's say we take vitamin C and we put it in a mass spectrometer, which is going to tell us the percent mass of all of the atoms that are found inside it. And then we get this spit out. So we've got carbon, hydrogen, and oxygen. And it tells us.
And so this would go on to tell us the empirical formula, and then we can get the molecular formula, and then look at analysis. So this is also another great video. He, in the Bozeman Science department, that channel has a lot of good videos for you to go and watch. And so you may want to look up his channel, subscribe to it. Notice over here on the right, he's talking about the mole. Okay, and so inside the Space Shuttle Challenger, that one's kind of cool. So we're going to go back to our video though, or back to our slide. And, oops, hopefully we'll go back to our slide. There we go. And so what I want to do is look at burning a hydrocarbon. And so it has some amount of carbon and hydrogen, I don't know what. and it produces CO2 and water. What is the empirical formula of this hydrocarbon? So the first thing I want to look at is burning. Burning is in oxygen, O2, and we're going to make CO2 and water. So we want to look at some of the things that we need to assume. The fact that my dog is probably going to bark in about a minute. First of all of the carbon made to make up the CO2 as our product comes from the hydrocarbon. And all of the hydrogen's mass found in the water also comes from our hydrocarbon. So let's say we have this puddle, 0.115 grams of this hydrocarbon, whatever it is. What we have to realize is that when we burn it in oxygen, we're going to make 0.379 grams of CO2, and we're going to make that for every 1 atom of carbon, we're going to make 1 molecule of CO2. So if we look at that, okay, because there's 1 carbon in CO2, and there is going to be then a 1-to-1 ratio. For every 1 CO2 made, we'll have 1 carbon in the hydrocarbon. With the O2 in the hydrocarbon reacting with the hydrogen, we're going to make water. And so for every 1 molecule of water, we need 2 H's in the original hydrocarbon, because there are 2 H's in the formula for water. So we're going to utilize these as conversion factors. Woo! Sorry, conversion factors are our friends. So let's look at this. First of all, we don't have grams of CO2 in moles. Get it in moles, okay? Because I have no idea what I'm doing, but let's at least do that. Now the moles of CO2 can get us some information. For every 1 mole of CO2, there is 1 mole of carbon. Or for 1 molecule of CO2, there would be 1 atom of carbon. It's easier to keep it in moles, so I would. And this comes from just intuition, the formula. There's 1 C in there. So for every 1 CO2, there's 1 C. Now let's get that in grams. So the moles of CO2 cancel. We have 1 mole of C. Let's get it in grams. Okay, well, we got it in moles. We can do the same thing for hydrogen. And let's do that. Let's get them in moles, because remember our empirical formula, we had to get them into moles and then look at the simplest whole number ratio. So now that we have the moles of carbon to hydrogen, let's divide by the smallest number of moles, which in this case is the 8.6116 times 10 to the minus 3. And this one was a 7, sorry. So that one was a typo. And so let's divide by that. And we're going to see that, of course, we're going to end up with 1 C here. And so we've got 1 C to every 1.33 H's. Now, this is not a simple whole number ratio. So if we look at the hydrogens, what number do you multiply 1.33 to get the next whole number? Yeah, it's a 3. So let's multiply both by 3. So we're going to get 3 carbons for every 4 hydrogens. And so our empirical formula is C3H4. Yay! Now here's percentage of 3 different chemicals. The molar mass of the entire molecule is 116 AMUs, or you can say 116 grams per mole. What is the molecular formula? Well, the first thing you need to do is get the empirical formula, the simplest whole number ratio, and then as with our other problems, we'll look at what does the empirical formula weigh, and then what does the molecular formula weigh. So, of course, get everything into moles. So I did that using the molar masses. Divide by the smallest number of moles. Oops. And so here I'm going to have, oops, that was weird. So I'm going to divide here by the 1.713, 1.713, and 1.713 to give me 1H, okay? And I'm going to have 7.99, oops, that was nitrogen. Wow, major typo there. Bad teacher. Okay, that's okay. Sometimes when you're typing late at night, you go all weirdness on it. And then we're going to get here 3 carbons. So woohoo, we got 3 carbons to 8 hydrogens to 1 N. So we'll see that on the next slide here. Here's our empirical formula. Now, our empirical formula weighs 58 AMUs, and the molecule then weighs 116. So, oh, man, I really like that factor of 2 there. So the molecular formula is twice the amount of the empirical. So C6H16N2. All right, that's it for section 3.9, empirical formulas and chemical analysis and molecular formulas. The next section, section 3.10, is on balancing chemical reactions. And so we'll get to that in the final video.